In this video, we'll demonstrate how to do inferences for simple linear regression using R. So I'm going to start with parameter testing, and we'll be using the check weight dataset, which is default built into R. I'm going to use CW just so I don't have to type out check weight a whole bunch of times. One of the annoying parts about the built-in check weight dataset is it has a capital C and a capital W, and if you forget to capitalize either of these, then R doesn't read that in as a data set. So a lowercase CW is going to work for me through this particular code. Now in running the model, so I saved a linear model, I'm going to use time, that is how long a check has been around, to predict how long or how heavy that little baby check is. So we're going to use time to predict weight with the check weight dataset. Now for our first test, we'll construct a test by hand. We'll do a test of beta 0 equals 20 with the null hypothesis versus beta 0 is greater than 20 for the alternative. So we have that the intercept is 27, and we want to see, is this statistically significantly bigger than 20 or not? Now where this would happen in real life is somebody might say, you know, I don't really care, like saying the chick weight at birth is positive, that doesn't really mean anything, right? Of course, once a chick hatches, they're going to have a positive weight. So that question isn't meaningful. But maybe what is meaningful is that this brand of chicken, maybe we expect it to weigh, maybe the average is 20 with other brands, but we expect this particular breed of chicken to weigh more than 20. So this is a case where that might happen, where 20 might be the minimum number that I actually care about for the intercept, which in weights of baby chickens would be the birth weight, or the intercept would be the birth weight. So in this particular case, we're looking to see if the birth weight is 0 or maybe it's bigger than 0, and we'll calculate this by hand. So first of all, instead of having to type CW with a capital T time and then a weight, I'm just going to use X and Y. Y is my weight, X is my time. And I know from my formulas that I have to calculate the sum of squares of x, y, so I'm going to do that. Note that I've wrapped the values in parentheses, and I recommend that you do this on your homework, because what this will do is not only calculate the value and save it as the variable ss underscore xy, but this will also print the variable, and it'll let me know where you went wrong if you went wrong, so that I can check your work as you're turning in homework. So we've got the sum of squares of x, and then I use them to I can predict B1, so B1 is sum of squares of xy divided by sum of squares of x, and I can check with the built-in function in R, does this match? And I see that my hand calculation of B1 matches the built-in calculation in R, 8.803. Then I have the calculation of B0, and again I see that this matches with the built-in calculation in R, 27.467. Okay, so my hand calculations of B1 and B0 work. Now because we've already done hand calculations of parameters, when you're doing the work for this, you can just pull the parameters off of the model if you want to. The work for this is primarily for the testing and calculating the standard errors and the test statistics and p-values and so forth. Okay, so for the sample size, I've got 578. That's how many y values I have. Y hat, this is going to be the prediction for each of the y. So remember, the prediction for each y is B0 plus B1 times each of the x values. So this is going to be 578 different predicted values for y, and the error is going to be the difference between the observed and the predicted values. So y is the observed values, y hat is my predicted values, or my mean prediction, or my expected value. Remember all those we talked about, y hat is all those. That's going to be my e, which is my residual or my observed errors. The sums of squares of errors, I'm going to add up all of those error terms and square them. That's my SSE. And then the mean squared error is the SSE divided by n minus 2, and we'll call it n minus 2 because we're predicting 2 parameters. So when I'm doing my test of beta 0, I need to calculate the standard error of beta 0. So the standard error of beta 0, this is the formula. I just typed in the formula, square root of MSE times 1 divided by n plus the mean of x, quantity squared, divided by the sum of squares of x. So I just calculated, I wrote all these variables out. Sum of squares of x is up here. Mean of x, MSE, I calculate right above. So and this is typically how I'll implement formulas in R, is for any long terms that I can shorten, like MSE or the SSX, I will calculate it prior and then just use those terms in my formula when I write it out so that my formula is a little bit more readable. One other thing I could have done that I didn't do is write like x bar as a variable and then just done x bar squared. But I can just use the mean of x. It's not too long to type out that way. In any case, the standard error of B0 I calculate to be 3.036, and we will check this against R in a second. Now for the hypothesis, I'm assuming that K is 20. That's the null hypothesis. So remember, we calculate the test statistic under the null hypothesis. We have the observed value of B0, which we calculate up here, minus the value of K divided by the standard error of B0. This was my test statistic, and again, I hope you can see how what I'm doing is I'm just working backwards. Well, for the test statistic, I need the standard error. For the standard error, I need the MSE, and I need the sum of squares of x. For the MSE, I need the SSE. For the SSE, I need the errors, and I'm just kind of working back and building my equations based on what I need. As you get more and more comfortable with these, you'll realize, well, if I'm doing anything that involves an error term, I just have to calculate the error. So you'll get used to calculating things like x, y, sum of squares of x, the parameters y hat, and e for virtually every problem you do, because you're going to need all these components eventually. So after I've calculated my t statistic, I can compare to the critical value. So if I do qt, and then 1 minus, let's say we're doing alpha over 2, so this would be 0. Let's say we're doing a 0.05 test, I guess, so we didn't list alpha anywhere, divided by 2, and then the degrees of freedom is going to be n minus 2. So this is my cutoff value comparison. So I can look at this cutoff value and say the cutoff value is 1.96, positive 1.96, because we're looking for greater than 20. So because this value is, so it shouldn't be divided by 2, excuse me, it should be this, so it should be 1.647. Shouldn't be divided by 2 because we're just doing a one-tailed test. I apologize. See, I got so used to us doing our two-tailed tests. But for a one-tailed test, we can see that the test statistic 2.45 is clearly greater than the critical value, so we would reject the null hypothesis. To calculate the p-value, again, remember we do times 2 for two-tailed tests, but in this case, we'll just do the regular test. I feed in, I use pt instead of qt. I give it my test statistic, the degrees of freedom. Now I'm going to use the argument lower tail equals false, so I don't have to worry about being upper or lower. And lower tail equals false, what that means is instead of finding the area below the test statistic, find the area above the test statistic. So on my curve, this is a positive test statistic, so it's on the right-hand side of my curve. The PT would by default find all of the area on the left-hand side of that test statistic, but I don't want the area on the left-hand side of the test statistic. I want something as or more extreme, so I want the area on the right side of the test statistic, and I can tell R to do that by giving it the argument lower.tail equals false. So I find the p-value for a one-tailed test of beta 0 compared to 20, or being greater than 20, is p equals 0.007. So this is clearly less than an alpha of 0.05, so we would reject the null hypothesis. Again, I multiply this by 2 if I'm doing a two-tailed test for at or more extreme, and then I may or may not use lower tail equals positive. I'm going to use lower tail equals false. I'm going to use lower tail equals false if the test statistic is positive and I'm looking in the positive direction. I'm going to not use lower tail equals false if the test statistic is negative. I'm just going to leave it at its default setting if the test statistic is negative. Or you could set lower tail equals true, because if the test statistic's negative, you're on the left side of the curve, and you do want to look on the left side, so that would be the lower tail component. All right, so how do we do this in R? Well, we've got to remember a couple things first. So I'll go on and run the R calculation. The R calculation is summary of the model that we made. So the model that we made, remember, just gave us those coefficients and reminded us what function we used. The summary actually gives us the estimates and the standard errors and the t-values and the probabilities. So let's look at this. So we already checked that the estimates were right earlier. For the standard error, we only calculated the standard error of B0. I think in your homework you'll do the standard error of B1 to test B1 against a k-value. So let's see, the standard error of B0, this is where we calculated the standard error of B0, that was 3.036. So 3.036 is the standard error of the intercept. So we calculated the standard error appropriately. Now let's check the t-value. Well, the t-value was 2.459, and the t-value in this is 9.046. So pause the video and take a second to think through, why would the t-values be different? This is correct, but pause the video and take a moment to think through why that would be the case. All right, coming back to look at this. Did you get it? Did you remember? So up here, the t-value is comparing against k equals 20. But down here, recall that the default built-in functions in R compare against k equals 0. So we can't use k equals 20 because that's going to be a different test statistic. It's a different test than comparing to 0. What we could do to make sure that our code is working appropriately so that we can double check is just real quickly use k equals 0 and then calculate the test statistic to compare to what R is built in, 9.046, 9.046. Okay, so when R is comparing to 0 and our code is comparing to 0, we're getting the same value. So I feel a little bit more confident that when I'm comparing to 20, I know it's not the same value because I'm not comparing to the same numbers built in R, but I feel a little bit more confident that my code is working because when I made the K the same value as what R was using by default, I got the same answer. So if I just change K and I don't change anything else, then hopefully it's still working for K equals 20 as well as it was working for K equals 0. That's true a lot of the time, and that's a good mental double check. It doesn't work all the time in case something in your code is specific to K equals 0 and only works for K equals 0. Something else depends on that. But for this case, again, it gives us a little bit of peace of mind. And then we've got the probability of t. So this is 2e negative 16. Just a reminder what e negative 16 means. That is 10 or 16. So that's what, 16 zeros, 0.000000000000000002. So that's our e to the negative 16. 2 times 10 to the negative 16th power. And actually, in this particular case, what we're saying is that it's even smaller than that. So the p-value is very, very, very small. So it is definitely statistically significant at the alpha equals 0.05 level. But again, recall that this test is against k equals 0. And remember, in our hypothetical case, we don't really care to say that chicks have a positive body weight when they're born. Like, that's not particularly meaningful. What we cared about is, does this particular breed of chicken have a higher body weight than this, say, national average of 20? And what we found with our internally calculated test statistic using our internally calculated p-value is that, yes, this is statistically significantly greater than that value of 20. So recall for interpretations that first what we do is we look at statistical significance. Now, if these indicated no statistical significance, that is, the p-value was greater than alpha, that isn't the case here, but just if they did, then what we would say is that time is unrelated to the weight of the chicken and that the intercept doesn't have enough evidence to conclude it's different than 0. After that, I couldn't talk about these estimates in terms of their numbers. I couldn't say, well, as time increases by 1, weight increases by 8.8, because I don't have enough evidence to conclude that this isn't 0. So I could say as time increases by 1, weight increases by 0, but that doesn't really make much sense, and it's really not worth talking about. So when we declare that something isn't statistically significant, that is, when we say that these numbers aren't different than 0, or we don't have enough evidence to conclude that these numbers are different than 0, there's not really much to say about these numbers specifically because we don't know that they're different than 0, and we can't pretend that we do by interpreting these values that aren't different than 0. However, in our case, these numbers are statistically significant, so we can interpret them. So as opposed to saying, well, the relationship between time and weight isn't statistically significant at the alpha equals 0.05 level, which is what we might say if it wasn't, we can say the relationship between time and weight is statistically significant at the alpha equals 0.05 level. And recall, we talked about several ways to do that. We could write p less than 0.01 or p less than 0.001. Both are true for this case. And then we can go on to then write interpretations about beta 1 and beta 0. So what we would say is that as time goes up by 1, our best guess of how much weight goes up by is 8.8. So that's our best guess. And then the weight at birth, our best guess is that the weight at birth is 27. Now recall that we also talked about how to create confidence intervals for these values. So we can look at meaningful interpretations of what these could be. So to find confidence intervals in R, you just use the convent function on your model, and this gives a 95% confidence interval for the intercept and for the slope. Now, some students get confused with this time label. This time label is it indicates what variable this is calculating the slope for. So it's just, instead of x, this is labeled time because time is the x variable. This is important when we have multiple x variables so that you can keep them distinct, but don't get confused. This is our beta 1 interpretation, or this is B1, our estimate of beta 1. So for the 95% confidence interval, what we could say is things like we're 95% confident that the true birth weight is between 21 and 33. So if we're comparing to a true birth weight of 20, we can see that the true birth rate of 20 isn't in this interval. So as we found before, we would call that statistically significant. For time, we can see that the growth in weight per each growth in unit of time, as time goes up by 1, the weight goes up by somewhere between 8.33 and 9.27. We're 95% confident that that's how much the weight goes up by. So though we can do a specific point interpretation for time, recall that this value is always going to be wrong. But the 95% confidence intervals often offer a reasonable standard by which we can say, well, we're pretty sure that it's going to go up between about 8 and 9 for every unit increase in time, or 8.33 and 9.27 for every unit increase in time. Confidence intervals offer a great way in which we can offer reasonable ranges of what we could expect. So it's reasonable to expect that the weight increases by 8.33 to 9.27, something in that range, maybe a little smaller, maybe a little bigger. 95% of the time, though, it's going to be between these two values. Or we're 95% confident that the true weight increase per unit increase in time is between these values. And again, this can be really helpful for interpretation because maybe 8.8 is a huge growth, but maybe 8.3 is a really small growth that we don't care about. So maybe what you would say is, well, there's potential that this is a really small growth that we don't care about. There's also a good chance that it's huge growth, and then there's a chance that it's an immense growth that's way bigger even than the huge growth. So we can use confidence intervals to present reasonable ranges as we're discussing interpretations. Note that when comparing to a null hypothesis of the parameter equals 0, that what you'll see with the confidence intervals is a negative number and a positive number if 0 is in the confidence interval. And one of the reasons that we have trouble interpreting with that is because that might indicate that it's reasonable to believe that the relationship between x and y could be positive or negative, or 0. There could be no relationship at all. And with that kind of a conclusion, it's like saying, well, anything's possible. Our data aren't really telling us or giving us much information because they're telling us, well, it could be positive, it could be negative, it could be 0. So time could increase the weight, time could decrease the weight, or time could not affect the weight. And if I told somebody that, oh, I really need to know, does my new program work? Or I really need to know, Is the SAT related to GPA scores? Or I really need to know if this new drug increases health. If I say, well, it could, or it couldn't, or maybe it's not related at all, or it could help, or it could hurt, or it could do nothing, then people would laugh me out of their office. So that's why when we have 0 in the confidence interval, especially if we're comparing to a null hypothesis of the parameter equals 0, that's where we run into issues and why we don't really focus on these kinds of interpretations. Because if you were to interpret it, your interpretation would look kind of silly, because it would say things like, well, it could, or it could help, or it could hurt, or it could not do anything. All right, so on to prediction. So for the confidence intervals, of course, you can calculate this by hand. We demonstrated one calculation by hand. I'm going to leave some for your homework. Prediction is going to be the same thing, but we will talk about how to do this in R because sometimes it gets a little confusing. First of all, we're going to use the predict function to do prediction. The first argument will be the model, and then we're going to write new data equals data.frame open parentheses. So what this is saying that the new data, how we have to feed new data for the prediction is in a data frame format. Frankly, I have never understood why this is the case. It's kind of irritating. I think that it's because if we are predicting when we have a model with multiple independent variables, we need a way to indicate what the values of each of the independent variables are. But it's still really irritating to utilize. In any case, this is what we have to do and why it's so important that we talk about how to do predictions using the built-in functions in R. Even though I know you're going to be potentially asked to do some by hand, the built-in functions can be confusing themselves. So we've got predict, we'll use the model, then the new data is the data frame. And then what we list here is whatever variable, independent variable we're setting. So this would be X, and I'm setting X equal to 5. So I want to make a prediction of what the weight will be at time equals 5. Note that this time variable is again the exact name of the variable that I'm using in X. So if this had a lowercase t time, then I would use a lowercase t time here because this has an uppercase t time in the variable that I'm using for X. Then this is going to have an uppercase t time in my predict function. So it's just that exact same variable name to tell R exactly which variable am I is this data for to predict. So again, this is like X sub H in our formulas. So if I run this, I get that at time equals 5, the best guess single number, the point prediction of the weight is going to be 71. So at time equals 5, my best guess is 71.5 will be the weight. Now I can look at the documentation, and in the documentation for predict, we can see a few different options that are available. One is interval. So interval calculation, we can either say none, which is the default, or confidence or prediction interval if we wanted a confidence interval or a prediction interval. Recall the confidence interval is for the mean response. The prediction interval is for a new point response. So I'm going to go on and predict the confidence interval. The confidence interval is between 67 and 75. So at time equals 5, I'm 95% confident that the average y value, the average of all of the y values, is between 67 and 75. Note that, again, for the confidence interval, I'm predicting the average value. Contrast that with the interpretation of the prediction interval. So the prediction interval is between -5 and 148. So this is a ridiculously large prediction interval. But what does this mean? Well, it means that at time equals 5, for a new point, that new point could be, -5 is below meaning, so it could be 0 weight, or it could be all the way up to 148. So there's a very, very wide range of values for weights for a new chick at time equals 5, versus this is for the average value of all the chicks. We're assuming their average value is between 67 and 75. 95% of the time, or we're 95% confident that the average is between this. So in this particular case, I want you to consider which one you tend to use more. And frankly, honestly, most people try to predict a new data point as opposed to predict the mean or find an interval for the mean of the points. So this prediction of a new data point tends to be the one that most folks want to use, just because typically we want to predict new data or a new single data pointer case, as opposed to trying to predict what the average is of all of the cases at that time. It's not that this is the only thing to do, that's why we talk about both, but it probably is the more common, is to use the prediction interval as opposed to the confidence interval, even though the prediction interval is a lot wider. And this is where you'll run into trouble, is people say, oh, use a narrower interval, this is way more helpful, this is way more useful to know it's between 67 and 75. And the problem is that if I put in a new data point, well, it very well could not be between 67 and 75, because this isn't a prediction interval. This isn't for a new data point. This is for the mean. In fact, this is kind of for the regression line. And we'll talk about that when we look at the graphic here. So when I'm doing a graphic to show an interval, what I end up doing is I create a range. I'm pretty much creating a plot. So I'm going to have my, I guess I'll go in and plot my data and my line. Now I want to calculate this confidence interval for each point on the plot, and then I want to draw a line that demonstrates how wide that interval is. So what I'm going to do is I'm going to list a whole bunch of different x values, and then I'm going to calculate the range, the low and the high side of the confidence interval and the low and the high side of the prediction interval for each one of those points. So first I'm going to find the range of x. So x goes from 0 to 21, and we can see that on our graphic here. So these x vals are the values. These are all of the different x data points. Now I'm going to do from 0 to 21. I'm going to do by hundredths. So this is a whole ton of different data points. This is 2,100 x values that I'm going to do a plot in. So I get a really high resolution line that I plot here. Now I'm going to calculate the confidence interval for the mod. I'm going to predict at all of those x values. So I'm going to have the time be every single one of those 2,100 x values, and I'm going to predict a confidence interval. So this is all of my confidence intervals for all of each one of those x values, and I'm eventually going to plot that. And this is the prediction interval for each one of those x values, and I'm eventually going to plot that too. Note that in interval, I only need to give it the first letter. How R works, or how many functions in R work, is that if you give it enough letters to indicate which option uniquely, then that's good enough. So you could just write C or P or N for confidence interval, prediction interval, or none. Or you could leave it blank for none, because that's the default. Okay, so now what I'm going to do is I'm going to have at each one of these x values, I'm going to plot a line connecting each one of these x values. So x is all of the different x values, and I do them in ascending order, because otherwise it'll mess up your plots. And then the lower confidence interval and the upper confidence interval are these two different lines. So I'm going to draw a line for the lower confidence interval and a line for the upper confidence interval, and I'm going to color them red. So here's the lower confidence interval. Here's the upper confidence interval, and it's kind of tough to see, but if you zoom in, you can actually see it get narrower in the middle and a little wider on the edges, and this is because if you recall that when you're in the middle of all your data, your predictions are going to be more accurate. Now the confidence interval is again for the mean response. So this is where we are 95% confident the mean of all of these data will come from. So what the confidence interval would mean for like time equals 14 is I'm 95% confident that if I took the mean of not just this data, but the population data at time equals 14, not just the sample data, but all of the data, I'm 95% confident that that mean will fall in between these red lines. Another way to think about this, because this line, this black line, is the expected value of y. This black line is the mean of y for each one of these data sets, is that the confidence interval, when graphed in this way, is kind of the confidence interval of where the line should fall. So these red curves, and again, they just slightly curve, they're a little narrower in the middle, a little wider on the edges, but these red confidence interval lines indicate a 95% confidence interval of where this regression line should fall. So we're 95% confident that the regression line should fall between these red lines, is another way to think about that. And that's because the regression line is the predicted mean response. So when we're talking about confidence intervals being the mean, well, the regression line is the mean for all the data taken together. All right, so now let's add the prediction interval. So that we're going to do the exact same thing for each one of the x values. We're going to have the y value be the prediction interval line. And let's see if we can spot a difference between the red and the blue. So we'll start with the lower and then plot the upper prediction intervals. And oh my gosh, you will see just how far out the prediction intervals are from the confidence interval. And again, think about this. The confidence interval is like, where is the line going to end up? The prediction interval is like, where are each of the dots going to end up? So the confidence interval is more like for the population line. And again, for each one of these x values indicates for the population, all of these different x values, if I took the average of the y's, for every x value at x equals 12, where would that average be? And that would be between the two red confidence interval lines. However, if I added a new data point, where would I be 95% confident that the new data point would fall? Well, that would be between the blue lines. And again, think about this. We mentioned the problem of if a boss asks you to use a confidence interval as to predict a new point, you can see that if I used a confidence interval to predict a new data point, well, there is a ton of data points that are falling outside of these red lines. However, if we look at the blue lines, you can see that, yeah, roughly 95% of the data are falling in the blue lines. Definitely more at the bottom than at the top, but taken as a whole, about 95% of our data is falling in between the blue lines. So if we're predicting an individual data point, again, we're going to use the prediction interval or the blue lines. If we're trying to predict where the regression line will be, or if we're trying to predict an average for the population over all of a particular value of x, then we would use the red lines to calculate the confidence interval for the mean response. This has been a video demonstrating how we implement inference confidence intervals, calculate confidence intervals for the parameters, calculate confidence intervals for the mean prediction, and calculate prediction intervals in R.